Yeah, I think we can just get started. I'm hosting, so I'll just say a couple of words about what we're going to be talking about, which are, well, I think primarily it's going to be about learning efficiently in hierarchy or with multiple LMs in general.
All right. You guys see that Word document there?
Yes.
All right. Um, let's go to the top. And again, I apologize for the sketchiness of all this. Before I even go into this, let me give you a little background here. One of our goals for this year is to understand how the cortex as a whole solves sort of complex goal-oriented tasks. And that problem, it has some similarities, I believe, to problems we have with learning. And that it's sort of like, how do we coordinate across multiple columns in the cortex? It requires attention, it requires the hippocampus for memories and so on. So I think that's how I got into this problem. I said, if we don't understand how the hierarchy learns, we're not going to understand how the hierarchy solves goal-oriented problems. So I said, learning efficiently in a hierarchy. The problem, which we've talked about many times, is that thousand brain theory assumes that there are many cortical columns. They learn similar or identical models. It's easy to understand how that works when we have a single column or single learning module attached to a single sensor. But when you have lots of columns all trying to learn the same models and they're not all experiencing or sensing something, it can get difficult. So, we didn't really understand from a practical point of view how many models could be learned. It's easy again with a single column. The problem got worse when we started talking about behavioral models, because with behavioral models, you don't even have the time for a single column to go around and sense everything. So there seems to be some way that if the cortex is going to have thousands of models of things, that somehow these columns have to learn them, even if they've never experienced the object or the entire object. Is there any questions about that problem, about that first statement there?
Agree that there's a problem.
Okay. All right. So then I said, there's a bunch of things we've been talking about that seem to be related. So these are just related things, potentially. One is that learning is always compositional. It's become clearer to me to think of it that way. We attend to one object at a time and we assign it to a location or reference frame. This can be very simple, like just you're attending the edges in V1 and you're building up applying to a reference frame, and it can be very complex things. I'm at an intersection, I'm looking at the cars and the people and building up a compositional model that way. And then it seems like we can only attend to one object at a time when we're doing this. So when we're learning, it's this number two. It's like learning seems to be kind of it's a one-shot type of process, but it's kind of serial. You got to attend to one thing, the next thing, and the next thing. I go into a new room, I have to attend to each new piece of item in that room one at a time to know where it is. I can't do it all at once. So we go through this. And of course, once you've trained a system, you can infer rapidly. You don't have to do that. But when you're first learning, it seems we have to attend to one object at a time. Number three, we've talked about attention being a process of specifying an area in egocentric space. I think this is going to be critical. I don't understand it yet, but the idea is you don't attend. When we move or attend or take the sensor, we're not really saying take a sensor move to some location. We're saying we want to get input from some location, and the brain can decide how to do that. So attention it's really sort of in an egocentric space somehow. And then the columns that are sensing in that space have information that they can use to infer and vote and reach a consensus. And if a column is getting input from outside of that space, they won't participate in this attentional mechanism. Another thing is we talked about, questions on that?
Yeah. Well, about attention. Is attention the output of the hippocampus? As in, the hippocampus says that this is the area that I want to attend to. Now go there.
I don't
Through the
know.
columns.
We do know that sometimes attention is subcortical, right? It's like
Right.
you can attend to something because something moved on your periphery, and everybody goes and
Right.
tends over there. Um,
That's true.
it's not clear to me. I would think that the hippocampus would be involved, but I don't want to go so far as to say I know enough about it. Um, that would be a good working hypothesis. That seems like if the hippocampus is always involved, um, that somehow it's involved in attentional mechanisms. But it could be lots of parts of the cortex. I don't really know yet. There's going to be some cortical model-based attention, um, and but there's also, but there's also going to be subcortical ones. So I guess I'll just leave that as an open question for me at least.
Yeah, I
Um,
was thinking it might relate to the kind of action output that we have from every column, where
Yeah.
we're basically thinking of that being maybe a target location in space, an egocentric space. So it's like a column in V1 might say, I want to be sensing over there next, and then you move your eyes there, or the finger says, I want to be sensing over here next, and then your finger moves to that location. But then with attention, it might be more of a global thing, like I want anything available sensing at this location now, or whoever's close should be sensing there now.
right. You just brought up an interesting topic, Vivian, because there seems to be a couple flavors of this, right? If I'm driving my car and and I'm not really attending to driving the car, right? I'm just doing the routine stuff, and maybe I'm thinking about something or talking to somebody. Clearly, the cortex is generating behaviors, and it's probably doing the way you said, like, oh, move your finger here and grab the steering wheel there, in these spaces. But I wouldn't call that, that's not to me like attention. Attention is like when the cortex, when the hippocampus gets involved, is we are going over here, and everybody, we have to figure out what's happening over here. It's a more of a global thing, or locally. I think you just said this, Vivian, but I'm not sure if I call those both attention. Maybe we could, but I've been thinking of the word attention is like top down. We need to, I'm conscious of it. I'll have a memory of it. When I'm driving the car and I'm using the directional stalk on my steering column, I don't remember that. I don't have any episodic memory of it. It just happens, and I keep going. But clearly the cortical columns are moving into that space and saying, push on this thing. So I know I've been sort of differentiating between attention, meaning the not only just specifying the space, but also like you're invoking the upper columns, the upper parts of the cortex, including the hippocampus. But the same similar mechanism must be going on when I'm just driving the car. Does that make any sense? I guess not.
Yeah. Oh,
Vivian, did that make sense to you?
Yeah, no, that's yeah, along the lines of what I was trying to say. Basically, yeah, the kind of more global, high-level attention might be the same mechanism as we use at the lower level for just moving the eyes and driving the car, but maybe more at the hippocampus level. But both of them output locations in egocentric
Right,
space that we
right,
want to sense at.
right. I guess the only thing is the question is when we use the word attention, do we want to include both of those, or do we want to include those, things that go to the top, the hippocampus? So I don't
Yeah,
know.
that's yeah, for me also. I don't have a strong opinion on that.
I have been thinking of the word attention, the global one, but I'm open to suggestions.
So a
Um,
clarifying question. When we attend only at one level. We cannot attend at both levels at the same time, or can we do that?
well, it depends what your definition of attend is. My definition of attention is the global one that's occurring, including the hippocampus, and I think you can only attend to one thing at a time. Clearly, if you include the things like the day-to-day routine actions that like I said, like driving a car where you're just doing the routine motions and it doesn't lead to episodic memory, you can do that simultaneously while you're attending to something else. Like I could be manipulating an object in my hand and rotating it, but attending. So there's movement of my hand, but I'm not attending to the movements of my hand or what the sensors on my hand are. I'm attending to what my visual system is looking at on the object. So the somatosensory cortex is touching and recognizing and moving, but I'm not attending to that. That's my definition. So, but you can do those two things at the same time, but I don't think you can actually attend to something novel at the same time. Like I can't look at I can't be building up two new compositional models at the same time.
But if I'm looking at a compositional object like a car and the door of the car, can I attend to both of them at the same time, or it would just be like either the car or the door?
The way I view it, it would be one or the other.
Okay. Only one
In my definition of attention, and we're going to get to this in the images in a moment. It's like, imagine you're at the hippocampus, right? And hippocampus says, okay, I'm looking for new novel compositions. And so I can look at the door and attend to some feature. I can attend to some feature on the door and then assign it to the door or I could be looking at, a building, a novel building, and assigning it as a feature to the intersection, or the block I'm standing on. So, to me, when I use the word attention, I'm just referring to sort of like, what is the next child object that I recognize that I'm going to put in some reference frame?
Okay.
It's like, right, that's how I'm viewing it. But these are complex questions. So, anyway.
Yeah.
I just jumped to number 4 here on my list. When we attend to an object visually, we can imagine what it would feel like. We touched it. And then the other way around, if we attend to an object via touch, we can imagine what it would look like. We've talked about this one. There's clearly some sort of global communication that's going on when we're doing these things, when I'm learning. Then this statement again, they're all conjectures, but I feel comfortable about this one, that learning something new always involves the hippocampus. So when we're learning a new thing, whether it's a new word or a new letter or a new building or a new something, a new tool, we attend to and we have an episodic memory of that learning process. We could say, yeah, I just saw that today. I was learning, I remember seeing it and thinking about it. But on the other hand, other parts of the cortex must learn at the same time as the hippocampus, and we don't have episodic memories of those. So V1 and V2 are clearly learning. So, but the episodic memories only exist theoretically in the hippocampus or the regions just before it. And we talked several ways that a column might learn, even if it's not getting direct sensory input. This is number 6. So I imagine I'm some column, I'm not getting direct sensory input, or I'm not getting input from the attended region. If I'm going to learn, how am I going to learn? Under the assumption that I'm going to somehow learn when I'm not getting input, that's an assumption, but it seems like that's what this whole thing is about. I talked about the idea that, you can have horizontal spread from a column that is getting input. Like I'm a column, a patch of cortex, and I'm seeing an edge, but the next patch over is not seeing an edge. So I could train that guy in the same thing I'm learning. We had a vague idea about sort of top-down training, like somehow, it goes up to the top and travels back down. So these are all vague solutions, vague ideas.
I thought one other idea we had was to actually use attention for this. So basically, columns that are not getting direct sensory input still know about where in space they're currently attending, so they can still build a model of at least relative locations.
Right. Well, that's what I'm going to suggest below, but I don't know how they do that. How do they know where they are? You know what I'm saying?
But they would just need to know where the attention currently is.
Well, okay, let me phrase it differently. I put a note in the college drawing about this.
Okay.
Imagine we have a retina and it's looking at an object, and some percentage of the columns are getting input because they're on edges of that object or whatever. And we say, oh, okay, we infer the object through flash inference. We infer the object. So now we know what the object is. Now the eyes move, and it turns out that now that a completely different set of columns are getting input. It's quite possible that since the eyes move, the image is sort of sparse in the retina, or the active areas are sparse. And so now different set of columns. Those columns at this point in time they haven't established a reference frame, at least in our current thinking, they haven't established a reference frame. So I'm now a column, and I'm thinking like, well, I'm just trying to do inference. I don't know where I am because I didn't, how do I know where I am? I don't even know what object I'm on. I couldn't know what object I'm on because everyone voted. but I haven't, in our current mechanism, we haven't established a reference frame for that object in this column. So that column couldn't make a prediction. It would be like saying, yeah, I was told we're on the coffee cup, but I haven't yet established my reference frame for the coffee cup, and I don't know where I am on the coffee cup. Or maybe you're saying I would know because somehow I know where I am in ego space. Well, I guess the question I'm asking, Vivian, is how would I establish the right reference frame if I'm in that column that hasn't gotten input yet? And I do know what other columns thought were inferring, and maybe I do know where I am in ego space, but I don't yet know where I am in my own reference frame. Does that make? I don't know if that makes sense to you, but it just there's some holes in that thing. It feels like.
So I have a question to what your scenario is, but first, just to clarify what I was thinking about, it was that basically as the eyes are looking at an object, like you saccade at different locations in egocentric space, that you paid attention to different locations in egocentric space. And for example, a column in the finger could pick up that signal of where in egocentric space you're attending to at the moment, and then learn those relative locations. I mean, I don't know if that's a better
Well, the
solution.
question is right. I think that's right. But the question is, if I have to, I could know where I am in egocentric space, but how do I know what? Remember, in the neuroscience, I have to sort of anchor the grid cells, and so how do I know how to anchor my grid cells? I can know my location in egocentric space, but my grid cells don't know what object they're on yet, right? And so they're sort of undefined. So how
But
would
in
I?
this case, wouldn't we be learning something new? So we're not
No, I was just talking about.
recognizing?
I was talking about something. I was just talking about inference, purely inference. Like
Oh,
I was
okay.
saying, this is a related problem, even in inference,
Yeah.
where
But even in inference, wouldn't you be able to anchor your reference frame based on a couple of successive movements?
right. But well, each column has its own reference frame. At least in our current implementation, each column has its own reference frame,
Yeah.
and they anchor. I wouldn't say they anchor independently of each other, but they're not tied together. We don't have them tied together anyway. So, I'm a column. I haven't gotten input yet, and everyone else has figured out we're on the coffee cup, but I haven't sensed anything yet. I have a model of the coffee cup, but how am I going to know? I have to form a representation in my internal reference frame of where I am on the coffee cup, but I haven't actually anchored my grid cells to the coffee cup yet.
Well,
I haven't.
that's what I'm saying in this attention proposal. That column would have gotten input already as well. It just wouldn't have gotten input to L4. It would have only received movement vectors.
But right. But movement vectors don't anchor your grid cells. They, I know I can know how the sensor is moving, but I haven't anchored my reference frame yet. There are solutions to this, but in my mind, the current theory does not explain how I'm a column. I can say, oh, I know where I am, and I know I'm in the attended space. I can know how I'm moving in the attended space. I can even know what my fellow columns thought was the object we're inferring, but I haven't established my reference frame for that object yet. So I don't know where I am on that object. I know where I am in the egocentric space, but I don't know where I am on the objects.
Is it possible that the anchoring of one column could help the neighboring columns anchor also through the
Right.
layer 6 cortical connections?
Yeah, right. It could. So I guess that's where I'm going here in the next little block of text here is that it seems like columns can't be as independent as I've thought of them in the past. They have to have some way. There has to be some way for these to coordinate with each other to say, so they all somehow anchor at the same time. But it gets more confusing for that, at least for me. But Rami, I think the next paragraph it gets to this point. I said a potential solution direction. Again, maybe none of this is all completely new because we've talked about these things in the past. And the idea is to assume that learning occurs simultaneously in many columns at once. And so somehow it feels like we want to go in a direction that if I have a fingertip that's moving over an object, that many columns in the somatosensory cortex and probably the visual cortex are learning a model of that same object at that time. this to me was certainly not something, you know, it was like, this was not obvious. I'm still not sure it's true, but it feels like this would be the, you know, if this could occur, if lots of columns could be learning at the same time, that would be useful. Then we could solve a lot of problems. And I said this requires that all columns are learning to know what the object is currently attended to. So that's not too hard because there's a voting layer, and that they have established reference frame for the parent object. That's the thing I was just talking to you about, Vivian. You know, it seems like for me to, if I'm a column that's going to be learning something that I'm not getting input right now, I may not even be in the intended area right now. I'm just a column, but I want to train on what someone else is learning. This is the idea I'm working on here.
Would that mean the same column would learn the parent and the child object?
No. Why would you suggest that?
Because, well, if it's required that that column has already established a reference frame for the parent object, that means it's already learned the parent object. And then,
maybe I typed wrong here. Let me see here.
or you mean the column one layer up has the parent reference
Right.
frame and is telling it to the top-down connections?
Well, no, here's what I'm thinking. Okay, right. I was being sloppy in my writing. Okay, I'll just be sloppy in my writing. I'm not assuming that a column knows parent and child, but the basic method of learning, if I'm a column, the basic method of learning is I have established a reference frame for parent, and now I'm receiving input that tells me what child is at which each location. So, if I'm going to be learning the mug while the finger, I'm a visual column and you have a finger moving over the mug, somehow for me to learn, I would have to establish a reference frame for a new object called a mug, and then assign, and then know what child object should be assigned to that different locations on that parent object.
Oh, okay. So in this case, the child object is the input to this learning column.
Right.
Okay.
Right.
Yeah, makes
So
sense.
my idea here is that the voting layer is representing the child object. That's the object I recognized. Oh, there's the rim or the handle, or there's the car. This is something I recognized, and now it's somebody else recognized it. It's below me, and now I'm trying to assign it to locations and a new reference frame for a parent object. So, right, you said it correctly a second ago. So if I've established, if I have the correct, I'm learning something new, so I have to establish a reference frame for the parent object, and I have to be moving around on that, and then I have to assign whatever child objects were associated with those locations. I mean, I could stop right here because everything else is getting even more speculative after this. But the idea is, can we come up with a way for many columns to be learned simultaneously? And it feels like when we are learning something new, and if we're attending to something, then this could be possible, because there would be only one attended child object at a time for the whole system. You know, in my definition of attention, like, you know, going from the hippocampus down. Maybe I could go through the rest of this text, but maybe it'd be better to just switch to the Excalibur drawing it for the moment.
Just to clarify, does that proposal mean basically all the columns, even the ones that don't receive sensory input at the time, could get both the attended region as input and then the child object ID through voting? And then
I don't know. I think the one thing that's clear, that the voting tells me what the child object is. Voting is basically you're inferring a known object. So that's the child.
Yeah.
Right. So how the problem then I see is, okay, anyone can see the ID for a child, but how do I know my reference frame? How do I know what reference frame to establish, and that I can come back to it, and you know that it's the right one, and you know, It might be simple in the end. In fact, I think it is. It's just really confusing for me to think about. Yes, my head's swimming to think about these things. But you just imagine this. Imagine I have a single finger and I'm touching an object. I'm learning, oh, we know how that works. The column getting input from the tip of the finger establishes a reference frame, and it's saying, oh, but what features is it sensing, and assigns it to those locations. Well, all I'm saying is at this point, if I'm attending to this, I'm really thinking hard about this, like I'm doing this in an experiment where I'm putting my finger in a box and I'm trying to learn. I'm just saying that there are many, many columns that are learning the same model in different modalities at the same time, even though they're not getting any input. And how could that work is the question. How could that actually work? If that's true, how would it work?
Yeah, if I'm just thinking, I keep switching between the attention location option and kind of what you're outlining here, and the top-down option, where basically the hippocampus learns a very temporary model of how things are arranged as you move your finger, and then is able to invoke different modality models lower down for learning.
Well, that is probably
I mean, you
true
wouldn't be
too.
learning them right away in the lower regions.
Well,
But
remember there was that research paper I produced a couple times that
yeah,
talked about it, right? So it appears that you are learning it lower down. It's just slow. So that makes a lot of sense. It's like, it's not just the hippocampus. It's not that the hippocampus is learning it and then sometime later we'll transfer it. It's more like, oh, everyone's learning it. Just the hippocampus is fast, and the other guys have to take a lot of repetition.
yeah, but it seems like there may be two mechanisms at play, because yeah, you might have the slow learning at the lower level, but then still you're able to do the fast learning of moving your finger on it, and then you open your eyes and you recognize which object you just touched.
Right,
And
right.
that couldn't have been from the lower columns that have
You're
already
right.
learned it.
You're right. Good thinking. Okay. Does that clarify things or just make it more confusing?
No, I mean, I think maybe there are two separate mechanisms for two purposes, kind of like you
Maybe.
said in that paper, that yeah, you can learn fast models up top, but then the slower mod, the lower
Well,
level.
you're basically saying, even if what you're basically saying is, imagine there's going from the top down, there's a scale of models, meaning like you definitely establish where in the hippocampus. And imagine they start the gradations of how quickly they learn. So at some point, that starting from the hippocampus down, you might have models. Maybe it's just the hippocampus, but below that, you don't have any models of this thing. And so when you come across this object again, you're going to have to go up the hierarchy until you find a model that's usable. So maybe it's just in the hippocampus.
Yeah, so like the first time you sense it, it won't be like first time you touch it with your finger, there won't be a model in your vision column. So you have to rely on the short-term model in the hippocampus. But then
But
over the long term, you might
right, but
learn it in both
the
places.
mechanism I'm talking about would still be applying, right? Would still be that all the columns are trying to learn,
Yeah.
right? They all have to have the opportunity to learn. I mean, somehow these other columns in the cortex have to learn these models. So the goal is like, okay, maybe they don't learn it very rapidly, but they have to have the mechanism to learn it slowly. And to have the mechanism to learn it slowly, they have to do these things. They have to know what the child object is, and they have to establish a reference frame for it.
Yeah.
So right, they're right. Well, those are very good observations that clarify my thinking a bit. Right.
The models in the hippocampus, they have to be known high level models, right? They cannot be like a series of pictures at locations of a very low level.
No, I don't think that's true because, well, it depends on what you mean by low level. So,
Like if it's an object that I couldn't really infer, and all I can sense is just a bunch of features at locations, does that give me a model in the hippocampus as well?
well, here's something I've said before, and I think what's going on here. The hippocampus, imagine you're the hippocampus, and you have some models, and then you come across something that is unpredictable. Like this something, whether it could be anything like, oh, there's a new person in the intersection, or it could be something low down, like here's a new letter in the alphabet.
Hmm.
The hippocampus needs to be able to, it gets involved in both of those. If I teach you a new letter, it's just a bunch of strokes. You can call that a low-level object, but you're going to be attending to each of those little features, and you'll be remembering it. You say, oh yeah, there was a little funny thing on top, this little diacritical mark, and so it feels like even if the model, it's sort of like all models come to the top. Eventually, I mean, you can't learn anything without attending anything new, even if it's a very simple thing. You have to attend to the components. So again, the idea is that the hippocampus or somebody says, hey, there's something over here that's unpredictable. Let me try to infer what it is. And it keeps narrowing down its attention window until it finds something that it can recognize. That could be as simple as a line, and you're learning a new character. Or it could be, a mug with a new type of handle, or it could be an intersection with a car that wasn't there yesterday. So it's sort of like, but it could span that scale. I don't see any, and both physical size and simplicity. It seems like it's involved in all those things. Is that believable, Ron?
Yeah, it feels like if the hippocampus is able to learn like memories of things, then it would need to be like if I have a very long sequence of features at locations that I couldn't really identify, I have a hard time believing that this would be in the hippocampus because it's
Well, what do you mean a very long set of features? What do you mean? I don't know what you mean by that.
like a set of observations.
Like what? Give me an example.
Just like 100 characters, 100 random characters, and I want to memorize all of those.
Well,
If
this isn't about memorization, right? This isn't about it is about learning new objects.
Yeah,
So
but new objects are made up of like features at some locations, and if I don't really have any idea what that object is, then they would all just seem like features at random locations.
well, they're not random. They have to be
Right.
learned, right? So there may be unknown locations, or you didn't know that they would be there, but they're not random.
Yeah.
I think, when you say 100, I'm trying to think like that doesn't seem right to me. It's like, for example, if I look at Arabic writing, it's just very fluid. It's all connected, I believe, if I'm thinking
Yeah.
correctly. And I don't know how to parse that. I don't have any prior knowledge about where to parse that stuff. Like, where does this one thing begin and one thing end? And I can't learn it. It's just like I can't just, I don't just study and go, oh, there's an up and a down and up and a down, blah, blah, blah. No, that's not the way it works. I'm sure people who speak Arabic know how to parse that thing. And they say, oh, no, this is one little section. Here's how you define it from the next section. So it isn't like this one really long thing. We don't learn like that. The objects we learn are simpler than that. And then we do compositions of them. So,
Well, even in Arabic, there's still spaces between the words. It's like English, but it's the letters are typed in a way where like you cannot really parse the
right.
the
My point
letters
is,
easily.
I'm saying the kind of example you're giving, I don't think it's very easy to do. I don't think it's doable. I don't get 100 new features, all of that. There's no context whatsoever. Even I've looked at, if you look at very complex Chinese characters, I can't see them initially and see the different components that a Chinese reader would do. And so the first thing I do is I try to do that. I might say, oh, maybe two strokes for the horizontal thing is a feature that's repeated, can I, something like that, or I try to break into the parts that I might learn. Anyway, I think that I don't see a problem. I mean, you're bringing up like, oh, I don't think the hippocampus can do this. I think it can, and so I don't think it can do with the scenario you just suggested, like 100, a new item with 100 features that I've never seen before, and they seem to be weird. that's to me like learning the Arabic or a very complex Chinese character. I can't really do that very easily. I have to learn simpler things first and build them up. Just like I'll leave it at that.
Yeah.
I think I'm not accepting your argument yet that it can't be done, but maybe you're right. Can I just switch to the CalDraw right now? Let me just do that, and then hopefully, oops, what happened to my CalDraw? Isn't it in there? Where'd it go? Where'd it go? Did I lose it? Somehow I lost it. Okay, let me go back into Slack and find it. You had it in there.
Research meetings.
Yeah, right. There it is. I think that was it there. Okay. This is can you see that okay? I don't know how to get rid of the thing on the left. Is there an easy way to get rid of it?
There's like a button on the top left with the 2 boxes and an arrow. Go more to the right. Right next to the title 2026 2026 01 14.
Right here?
No,
This
it's
thing?
the right.
This
Let me see
thing?
if I can just point it out. Here.
Oh, there.
Yeah.
Oh, there you go. Thank you. Yeah, obvious. So this is some text, which is, I already stated, like giving the context for this problem. One of our goals is to get a theoretical understanding of how the cortex solves goal-oriented behaviors. And I'm saying there's similarities between solving goals and learning in a hierarchy. Both require tending to objects in temporary arrangements. Both seem to involve the hippocampus. Both can involve different sets of columns and modalities. So I said, understanding how columns interact when learning is not only similar, but I think it's necessary to do that before we can think about task solving. So I think this is all we have to have a better theory about how columns interact is in general to solve goal-oriented behaviors. And then these are some of the problems we were just talking about. How do columns learn complete models when they're unlikely to observe all the locations on all objects? And how this got worse with behavioral models. And so the basic premise that we're exploring today, there seems to be a need to train columns that are not currently receiving input. So then I talked about this, during inference, this is the issue about the retina and how different columns are exposed when you're moving your eyes around. So I want to talk about that. Now, I don't know, I didn't look at your drawings, Hojea, if you want to talk about them or not, but I do these drawings to sort of as sort of a way we could discuss the problems in a visual sense, to talk about, what are these problems we're talking about, and have sort of a visual picture of what might be going on. So given what you know, should I go with this, or do you want to do your thing first?
Let's do this. Mine is an example of the paragraphs that we skipped on the document. That is precisely the figure that I guess, like, at least that was what was happening in my mind. So I can.
So maybe that's more of a solution proposal.
No, it's just an illustration of what you were talking about, literally.
Well, and maybe it's the same kind. Maybe I'll do my illustration, and then you do yours, and we'll see if they're maybe achieving the same thing. So in the document, I just started. I said, let me just draw. Yeah.
Or can I ask a quick question first? What question I had earlier to the kind of problem about different columns getting input at different points in time. Like point to the
right here
related problem. I'm not sure I understand the problem. Like, wouldn't normally the same set of columns in the fovea get the input if we're attending to different locations in space? Because we always, I can't really think of a realistic scenario where I'm attending to a different location than where I'm saccading to. Or do you mean like touch and vision together?
No, I meant like, and maybe I'm wrong about this. So let me tell you what I meant, and then you can correct me. If you the phobia complicates things. Imagine you didn't have a phobia for the second, and you just had this, you have this retina and you have an image on the retina, and imagine there's a bunch of columns looking at different patches representing the image, sampling the image. Well, only some of those patches are getting, will be active, meaning they have, the center surround activation. And a lot of them, surfaces and blank areas, whatever, are not going to be getting activation. So the actual columns that are receiving an active center surround is a small subset of all the columns.
Yeah.
And then I move the retina, and now that, maybe that image is now a different part of the retina, and it's very likely that most of the columns that were getting input before are not getting input now. Some of them might be, but many aren't, and many of the ones that weren't getting input before are now getting input. If you think of the output of the retina, the optic nerve is pretty sparse because it's really just the center surround, active center surround columns that are outputting anything. It gets complicated with the phobia, and I think that might be part of the solution, but I don't understand it, because the phobia is very, very high acuity, and there's still lots of little columns they're representing the phobia. So can we make this same assumption about sparsity in the phobia, that only a small subset of the columns representing the phobia are active? I don't know if that may not be true. I don't know. Just don't know.
Okay. Yeah, I didn't think about the on-off receptive fields, and that even if we are attending to this phobia, many wouldn't get input. So yeah.
Right. Just imagine looking at a line drawing, right? And imagine you're looking at a line drawing of a face, and then you shift that face on the retina. The lines are almost, the vast majority of them will be on new columns, and most of them will be inactive, because with a line drawing, it's easy to imagine that.
Yeah. Can we assume that the ones that got input on the first step and then don't get input after the movement, that they still know where they moved, so they can kind of at least shift their location?
That's what my assumption would be.
Yeah. Okay.
Right. But then there's complications there too, because imagine there's a subset. Let's say there's 100 columns, and 10 of them say, "Oh, we're getting input. We decide this is a face or this is a mug." And now the image shifts. They know that they're a mug. They haven't forgotten that. And now they know that how the whole system moves, so they know where they are on the new object. They know where their new location on the object is. So what's the problem there? The only problem there is, if I want them to continue learning, then if they're not getting input, I want them to learn something else. It's like, otherwise they're sitting there doing nothing. Right? I say, yeah, I know I'm on the object. There's nothing there. Nothing on that. So then we're sort of back to where we started with, that.
Well, would they need to learn anything if there's nothing there?
No, but the point is, the next observation, we want every column has to learn the models of all the points, right? Our current theory says that I need to learn complete models, and so it would take a long time if every column has to observe every point on every object.
Yeah. Okay. That's back to the problem.
That's the premise, right?
Yeah.
Right.
Okay.
Again, I'm not going to take a strong position about any one of these ideas, because is it possible that, I don't know, maybe there's some other way to solve this problem? I don't know. It just seems like is an issue. And it really became the forefront when we talked about behavioral models, because with morphological models, we can sort of finesse our way around this. We can say, oh yeah, I have to move my fingers a lot and whatever. I don't know. But or it goes up, maybe it goes up the hierarchy and comes back down again. I don't know, Vivian. I don't know the answer. Okay, so
yeah. Okay, yeah, no, thanks, but that answers my question.
Yeah. Here's just a drawing that I attempted to sort of picture this. I show, let me do it with my little drawing figure here. Where's my little drawing thing? Because I haven't used this in a while. The laser pointer, right? K, I can remember that. So I got region 1, region 2, 3, 4, 5. I showed them getting smaller because that's the way they work in the brain. It's much more dramatic how much smaller, V4 is than V1 and V2. I've shown the hippocampus here as well, and I've shown this a series of single columns. We talked about that recently as well, that it appears to be this way. And these, by the way, I say there's scale 1 here and scale 2 here and S3 scale and score. I don't know if that's true. We do know that there's apparent difference in scales as you go up the hierarchy. The columns seem to be representing larger and larger areas. We see the same kind of scale change in the different columns in the hippocampus. So this is just a picture of what our current understanding, but it's kind of weird. It's sort of like there's a whole replication of scales here to match the replicates the set of scales down here. It's not like these are all, that would imply that these columns in the hippocampus aren't just the top of all these things, but somehow they sort of parallel these things, but I don't know. This is weird. I also put this little yellow area in the middle here to represent the phobia. And I point out that the scale of columns in a particular region, such as V1, is not constant. It varies quite a bit. The scale of columns in the middle are very small. That means they're very high resolution. But the scale of the columns on the periphery of V1 represent very large areas of the retina. And in all these regions, at least in R1, V1, V2, and V4, the entire retina is represented. So there isn't like, V1 only looks at the fovea. No, V1 covers the entire retina. It's just that most of the columns are focused on very, very center of the retina, and they have high acuity, and they have, they have one. That's when people talk about the scale, they're mostly talking about the foveal area. And there's a similar sort of foveal area in V2. I don't know enough about the other regions to know if that continues on. So this is adding a few layers of complexity to things we've talked about before that we've kind of avoided some of this complexity. And I'm especially intrigued by the idea of the hippocampus having these different scales, but they only seem about one column each. Strange.
What's the evidence that the hippocampus has different scales?
I'm sorry, it's the entorhinal cortex. It's the grid cells.
Okay,
It's the grid cells. So the assumption there is that the column equivalent in the hippocampal complex is entorhinal cortex has the grid cells, and hippocampus has the equivalent. The place cells are sort of equivalent of layer 4 type of thing, roughly. Okay. And so it's the grid cells that just determine the scale of the reference frame. Down here, when they talk about scale, they don't think about reference frames. They're not looking about grid cells, so they're just looking at what the cells respond to. So it's a little apples and oranges there.
Okay.
Then, there's this question like, well, we talked about, here's a second drawing here. This says, okay, imagine this region 2 is learning something new. It's the parent object, and as we move through the space, R1 is essentially voting and recognizing child objects, which are now going to be part of the new compositional object in S2. So some image comes in or some pattern comes in. Some of these columns, not all of them, get to vote. Only the columns that are active get the vote. That's the up arrows here. Some subset of the columns get the vote. They establish a child inference. I say, oh yeah, we know what this is. This is, the car or whatever, the handle on the mug or the letter or something. And now we're building a compositional object in R2. And so we're taking this child object ID and we're assigning to different locations. It changes as the sensors move. And we're assigning it to different locations in the parent object as we do this. So that's been our sort of basic thinking about compositional learning. You have 2 regions like this, and they work in this way. So that's nothing new there. But we're saying, but it has to occur all the way up to the hippocampus, right? So it doesn't just happen in 2 regions down here. Somehow the hippocampus is involved. And so then I said to myself, well, yeah, what's happening there, right? How's that work? And so I said, and I wrote that here. If learning a new object always involves the hippocampus, how does this work? You know, the child, in some sense, if I'm the hippocampus and I'm attending to something, going back to Rami's question earlier, let's say I see a new letter or a new variation of a letter in my alphabet. Well, normally the representations of this I would deal with are pretty low down in the cortex, maybe V1. And so somehow I have to be learning like, oh, I'm learning a new letter up here, but I also want to be somehow, you know, these guys have to train down here too, right? Going back to Vivian's comment earlier. I do need to train down here. I have to learn these models down here, even if initially I just learn them up here. So, how does that work? How do I do this here at the same time as I'm doing this here? And how does this work up here? Are these different scales? So it's mind-boggling to me. And this is the point where I just threw up my hands and said, oh yeah, I have to take a break. Don't worry. I think the answer will be pretty obvious and simple in the end, but it's the moment it's really confusing to me. So unless if anyone has a question about these diagrams or suggestions if they're useful or not, then maybe we could look at what Hojea wrote.
I just maybe one thing to mention here. I was thinking of the hippocampus as processing the highest level of information, like the object in the highest level. Like if I don't know about the intersection, if I don't understand the intersection, then it can only process features as being cars. If I don't know about cars, it will only process wheels. So that would maybe suggest that you would still be able to send those low-level features to the hippocampus, because that would be the memory of the highest level thing that we're learning.
I think that's right. But it should be like I know cars, but this car has something unusual on it. I'm not sure
because it's unusual, then we don't really understand that this object. Then we can still learn that in the hippocampus, because those features are the highest level representation of the object.
I'm not sure if you're agreeing or disagreeing, and I'm not sure if I would either. When I say the highest level, I think what happens is when we come across something that doesn't fit a model, any model, a simple model or a complex model, it doesn't really matter. It draws our attention to it, and then that somehow gets up to the hippocampus. Is that consistent with what you're saying?
Yeah. I'm saying it's we don't understand this inconsistent feature because we don't really have a model of that object, and we just have to send up the parts that the model is made of, because we don't really have a model of it. We don't have.
Or I agree with what I said, but it might be a slight distinction to say I might have a model of an object, but there's an additional detail I hadn't noticed before. So I might have a model of what some car style is, and I've been using it for a long time. And then someone said, "Oh, but did you notice that the hood ornament has this funny little thing?" And I go, "Oh no, I didn't know that." And so then I'm focusing on that hood ornament, and I'm sort of adding an additional feature to the existing model. I think about trees like this. Go ahead.
Does that change the parent object itself? Like if I'm looking at the door at the car, and then I notice, that this car has specific types of wheels that I didn't notice before. Does this make it a unique class of
No,
objects?
I don't think it does. I think it's just you're adding details to an existing object in that case.
Okay.
It's like saying, oh, here's another feature I didn't store before. There's a lot of things we learn where we don't learn all the details, but I could if I paid more attention to them. So it's not always like, oh, there's some feature I don't know. I don't understand it, but it's like I used to think about leaves this way on trees, right? You can look at leaves and you just say, oh, that's a leaf, and this is another leaf. That's a big leaf. That's a small leaf. But then when you get into it, you realize there's these details which are very, very, they're noticeable if you pay attention to them, and they help you differentiate trees and different types of leaves. And my point is that those features are there all along. I never said, "Oh, there's a problem. I can't predict these features." It was like, "No, good enough. It's a leaf." It's and it's sort of like a car. You could say, like, "Oh, this I know what Toyotas look like, and or this particular car, and then someone points out there's an additional thing I never noticed before, a detailing. Oh, it's been there all along. I just never paid attention to it. Now I pay attention to it. I can add it to my model." So it's not really a new model.
So what if you already have that feature in your old model, but that feature had changed on a new object? Like you
Right.
already know about the wheels, and they look a certain type of wheels that
Right.
you know about them. But then you notice on a new car that it's a very different color or something that you haven't noticed before. Would you like make a fork of that
Right.
object and start to create?
Maybe. I don't know. That now we're getting back to this question about classes of objects.
Yeah, that was just
And we don't know the answer to that question either. So I don't know the answer to that question.
So, about classes, you move on to my diagram, but about classes and class IDs and object IDs, I feel like just observing how we learn things, that we are learning class IDs and then only kind of spontaneously kind of like define strict object IDs as needed. Like if I only ever had TP mug, then I will just say, let me bring my mug. But now because I have to differentiate between Numenta mug and TP mug, that's how I kind of create like a new sub
I used to think that,
category.
but I put a note in Slack this on Friday after the note with the text block. We just went through, and had a different idea about it. It struck me that one possibility is that classes are defined by functionality and not by morphology. In some sense, they're defined by what an object does, not what an object looks like. And so a mug is something that can contain liquid that you can drink from, something like that. And so, there could be something that I might class as a mug could also be classified as something else. It could be classified as a shaving dish or something. I don't know. It's like I could use it as a mug. Or you can have objects. You could have two classes for it. But I just threw out the idea in that Slack post that it seems to me that functionality defines what a class is, not its shape. Now, shape could be related to functionality, of course, but and then I said, is it possible that behavioral models of some sort are really the definition of a class? So a stapler is not a particular staple; it's something that staples. And a mug is something that holds liquid you could drink from, and cars are things that propel you from one distance to the other. And some cars are 3 wheels, some cars are 4 wheels, etc. And so that was an alternate way of thinking about classes. It gets around this morphology issue.
Yeah, I feel like we talked about how maybe like affordances define
Right.
classes or
Right.
IDs. I feel like the way that our human brain just assigns IDs are just so not random, but kind of inconsistent. Like for example, like leaves, and if I have the ID as leaf, then that's good enough for me, and I don't need to know what particular leaf that is. But if I were forced to study like this might be offending a lot of plant biologists, but if I had to distinguish, then I would actually kind of try to go in and try to distinguish. Okay, this leaf is a maple leaf, and this is a pine
Well,
leaf.
let's
I
talk
don't
about
know.
leaves, right? Because there's lots of things that are leaves, not just things that grow on trees.
Right.
Leaves have this sort of, if I think about trees, or things that the tree grows every year. Some leaves look very different than others. Then I have deciduous and non-deciduous and evergreen type of leaves. These are all like, does it fall off or does it not fall off? And so and then we have leaves on grass and leaves on pieces of art. And so the idea of a leaf seemed maybe more of a sort of a functional behavioral aspect to what counts as a leaf, as opposed to what it looks like. And now an oak leaf, a black oak leaf looks different than a pin oak leaf. And those are East Coast trees. But those are morphological, specific models, more like specific. I think they're specific models. Of course, not all.
Yeah. I guess my point is that I don't think, for me, neither morphology or behavior really kind of defines the class or object ID.
Well, okay. Can you give me an example where sort of this behavioral idea doesn't define a class?
I think the example that I always have in mind is a medicine ball that people sometimes use to sit for better posture. So instead of chair, those like bouncy gym balls.
Right. So why is that? That's in my mind seems to fit well. So why do you think it doesn't fit well? I would say, I can call that ball could be a chair, right? It could be a poor table. It can be a piece of exercise equipment. So the morphological object has different classes that could belong to. And those classes are defined by how it's being used and when it does. It's more of a functional class.
Okay. But I guess I wouldn't normally classify that as chair.
No, but it could be. I mean, obviously we wouldn't normally do it, but if I'm trying to think of I need a chair and I walk into a room and I see one of those balls, I'll go sit on it. I'll just do that, right? I don't sit there and go, hey, that's a medicine ball. You can't sit on it.
Right. But
I mean,
okay.
I'm not sure. Right. I mean, right. If you right up front, would I say it's a chair? No, but I could say, but it could be, imagine you're doing you're doing a little capture thing and it says, okay, click all the boxes or something you can sit on. Right. So the ball would qualify as that, like a big ball. It's not a marble, but a big ball. I don't know. It's just an idea. I like the idea because there's clearly some validity to it. There can be huge variety in morphology for something in a class of objects. But what they all have in common, all staplers have certain things in common. They have staples, the staples come out, and those staples go into something. Every stapler has that. And beyond that, they can look like anything, really. At least that's the argument. I'm not sure if it's true, but
yeah. Okay. Well, I'm gonna, I guess, share screen if that's fine.
Sure, I'll stop sharing. Vivian, I'm expecting you at any moment in time come in and explain all this.
Just to clarify, did the pictures you showed now, did I miss it, or did they show how the shared learning problem could be solved?
No, I don't. They don't solve. I don't have, as I said in my post last night, I don't have a solution.
Okay, it was more like stating the setup and constraints.
And I'm just trying to make pictures to help us think about it.
Okay, cool.
Right.
Yeah, we're waiting for the solution from you. Here's some pictures to help jog all our noodles in our skull. But that's what I did. Yeah, so I had kind of two things. One was an example that I had in mind when I was reading Jeff's document, and then the other, I think, is just my restatement of the problem in my own words. So I don't think neither are very useful, but maybe, I don't know, a different picture or a different way of putting it, I don't know, might again spark some ideas. So that's the hope. And I'll start with this example. Again, this doesn't propose a solution. How do I zoom in? Oh my goodness. Okay, there we go. All right. So if you read like Jeff's the part of the document that we skipped, we talk about how Jeff talked about how there's like multiple levels of the hierarchy, or multiple columns may be learning at the same time, but the line between which regions are learning and which are not could shift depending on what you recognize.
Do you want me to rephrase that?
Yes, please. Yes.
What you said is correct, but I was making the observation. Imagine you're in the hippocampus and you need to attend to something. You're going to narrow down to something is recognized, and then that's going to be a new child object. Well, where is that being recognized? It could be recognized very at a small object. We were talking with Rami about like region 1, or it could be a mid-sized object, region 3. It could be a large object like a car, which might be at the top. So where the child object is recognized could shift based on the area that you're attending to, and so it's just the point of if you drew your figure backwards from mine, you have the hippocampus on the left, I had the hippocampus on the right. In your diagram, so imagine the hippocampus is always learning some new composition. So it's always going to be, getting new child objects and placing them in some reference frame. But where that child object was recognized could be all the way on the right on your diagram, or it could be just to the right of the hippocampus. And so there's this line between where the child is being inferred. You keep sliding to the right until you infer something. That's the basic idea. So it felt like, hey, beyond, once you've gotten to the child object that you're trying to learn as a new, the object that you recognize, that you probably wouldn't be training those columns there. They're inferring the child object, so that you can't. How can you train them? You want to train the things above that. At least that's the thinking was.
Yeah.
I don't know if it's true, but that was the idea. Of course,
Yeah.
this is Hangul, I assume. So.
Yes. It's so yeah. I assume that people don't know this, so you can try to engage, try to step back and think what your hippocampus is doing as you're looking at this, or your cortical columns are doing. So first, I always assume when you look at this word in the hippocampus, you don't know.
Is that one word or is that 2 words?
It's 1 word, 2 syllables.
Okay.
Okay. So it says hello, but the hello is like made up of 5 different like characters. It's kind of like that. So again, how's this division kind of? I mean, I know Korean, so I made this division. So again, I see this, I don't recognize it, so I'm gonna try to focus on 1 syllable at a time. So it could be this one or that one.
Do you know the 2? You're assuming you know the 2 syllables, and then it's just a new composition.
For now, let's assume that, but we'll go back to a case where we don't know how to make this kind of division.
If I knew the 2 syllables, and hippocampus said, "Oh, that's a 10." Oh, I see. There's a syllable. I don't know what it is, how to call it. The one on the left, and there's a syllable on the right, and I've made a new composition of those 2 syllables.
Yes.
Okay.
So for me, like if I see a new Korean word, that's what I would do, because I can try to, at least if I want to pronounce it, I can try to just pronounce like 1 syllable at a time.
Can I just ask a question? Are those syllables, do you know them all, or is there really a large number of them? Like syllables in English, there's quite a large number of them, but.
So
like, there's like 100 syllables and that's it? Is it like that, or is it not like that?
You can mix and match different vowels and consonants to make different syllables.
Okay, so it's complicated.
Yeah. So it's complicated.
And those each of these has 3 little components. It looks like. Are those? Is that right? And what would you call those?
Yeah. So each of so you're at 1 syllable, and then the next level, or kind of even more going into detail, I'm gonna just like move this away because I'm gonna assume that we're just attending to one syllable at a time. Again, we can't learn both at a time. We're just learning one thing. And even this, it's like, oh, this is complicated. I need to divide into kind of 3 different regions. So in R2, R2 represents the characters. So typically, I mean, you don't have to know this. This is the consonant. The circle is a consonant, and this incomplete H is a vowel. And this also the thing on the bottom is a consonant.
Is the physical arrangement important, I assume?
Yes.
So
Yeah.
there's a 2D arrangement of consonants and vowels?
Yes.
Wow.
Yeah.
So
yeah,
you could rearrange
know-
those 3 symbols and it would say something else?
yes. So let's say I switch to the consonants. Oops. Then that's a
Right.
different. Yeah.
Okay.
That's a different different, I guess, syllable, and like I would pronounce it differently.
So can you basically like phonetically read it out based on their arrangement, or do you need to recognize the syllable?
You can phonetically read it out loud.
Okay. So it's kind of like letters in Latin,
Yes.
and it's just arranged
Yeah.
in 2D.
A 2D,
Yes.
2D letter arrangement.
Yeah.
Do you
but I
read
guess
it like top to bottom? Like, is there like a grid reading for in which order you would pronounce them, or?
yeah, mostly like top left to bottom right. So I will try to pronounce this O first, and then I would try to pronounce this H, and then I'll try to pronounce this, I don't know, half rectangle. I have no idea what it was. How,
Do they have names? Do they have names in Korean? Like those?
yeah, it's like ABCD, and there's, so there's equivalent to ABCDs for these things, but yeah.
Can you just say those 3? Just what would it sound like?
The whole thing together is called. Okay, so this whole thing is 안녕. An is coming from here, so that's 1 syllable. The second syllable is young. So if you
Okay.
say
And then
안녕,
the an
yeah.
it's got 3 components. So how does that?
Yes. So this is called ung. The circle is called ung. The vowel is called a, like just opening up mouth. Like I'm saying with assuming like a circle consonant, like a, opening a, and then this bottom rectangle is like an N, like a. So it's like AHN if I were to like Romanize it.
Okay.
Like pronunciation of it. An, sort of, yeah.
Thank you.
Anyway, so yeah, so this syllable is made up of 3 characters, and then the characters themselves are not that complicated, but you can say like you can even dig deeper and go into the strokes and say, okay, this vowel is made up of 2 strokes, 1 vertical, 1 horizontal. Same for this one, but maybe the difference is that in this R2, the arrangement of these strokes is that the horizontal is in the middle for this one, and then here they meet at a quarter. I don't know. Yeah. Oh gosh, what was I going to say afterwards? Sorry, let me just gather my thoughts. Hold on. It just like completely stopped afterwards.
Well, I think I get. I mean, for me, if I was to learn this, I would be starting at the right end of this picture here, and I'd be trying to say, "Oh, there's this your in thing. Or the thing that looks like a little bell." I say, "Oh, that's 2 strokes." I'd recognize 1 stroke sort of curve and 1 sort of straight, and I try to remember the position relative to each other because I don't know that as a character.
Right.
The O one, the circle one. Well, I know what that is. I've seen circles, so then, but I'd have to. And then the half H, I'd probably have to learn that separately too, because then you have another one on the right there, which is got 2 lines going the other direction. So
Yeah.
so as a non-speaker reader, I would be starting out at the very, very bottom here,
Right. But yeah,
and
so
engaging my hippocampus in doing so, right?
yeah,
Like right now,
but
I have remembered that little curvy thing. Yeah, I just remember we talked about it.
yeah, I feel like when I'm learning this, I'm not actually like, I don't know if I'm actually drilling it down in this manner. Like,
You wouldn't have to, right? There's no reason you have to. You
yeah.
recognize the whole syllable. In fact, I'm sure
Well,
you
yeah,
recognize the
but for
whole
me,
word.
like, yeah, for me, I do. But like, if this was new for me, I feel like, I would learn individual strokes and try to put together, their spatial arrangements to get this letter. But that's really hard because there's a lot of individual strokes and a lot of arrangements. What's actually useful is that I recognize, oh, like with practice or, repetition, I see that, this combination of H's actually appear in a lot of places and learn this grouping of R2. So it's not that I recognize an HC, I don't recognize an R3, I don't recognize an R2, so I want to go to R1. It's that R1 kind of directly builds the model in HC, and along the way, we're also building kind of groupings in R2 and R3.
Well, this is really not different than learning a Roman alphabet like English, right? I mean, it's the same basic thing. We have individual letters that are composed of one or more strokes. They have a certain arrangement. You have to learn those first. Then you learn simple combinations of them. And then, then you learn combinations of those combinations. It seems very analogous to
Yeah.
in 2 dimensions.
Can I offer a contrast just because it feels like my brain went through a process that's different than what you two did?
Sure.
Okay.
So when I
Yes.
was looking at it, I was like, I'm imagining like how I reproduce it. And I
Yeah.
saw there's a grouping of 2 things and each of them has 3 things. And that's all I remember. And then I have visual memory. So I am literally in my mind's eye seeing the screen and reproducing the pattern.
It's interesting, Tristan, there's this big debate in education, at least in the United States, about about 2 ways to teach reading. And one is the one that I learned as a kid, where you start with the letters and then you build up from that. And the other way is they don't do that. And a lot of kids these days learn to read by just recognizing entire words.
Yeah.
And then they make lots of spelling errors because they actually never learned how to spell the word. They just learned what it looks like.
Yeah.
Which sounds like what you're doing, Tristan. Sounds like you're doing sort of the whole picture type of learning.
Well, part of the reason was because I'm assuming it was unfamiliar language, so that we would not be learning a language, but just an arrangement of unfamiliar things. And so when it was an arrangement of unfamiliar things, that's how
Right.
that's the process I went through.
Right. Well, I think it's very analogous to the debate about learning to read here in the States.
Can I ask you guys? Yeah, go ahead.
I guess maybe a different way to phrase it is, if you just see this and you don't know these are letters and the components appear in lots of other places, you might not invest the time in learning detailed models of each individual component unless you really need to. You just learn a rough approximation of the big picture.
Yeah. So related to that, did you guys notice that this consonant appears here as well? Like this corner rectangle is the same consonant as this. So, I mean, even in this one word, there's actually 2 of the same consonants, and same for this O as well. So I don't know if that's like a thing that you noticed because I pointed out, or like, oh, like you realize, okay, in our different like R2s, there's actually 2 objects with the same ID. Like this, there's this ID.
That would require first learning that little rounded half corner. A rounded corner is a thing, right? You have to see, oh, look, they look similar, and therefore it's a separate object.
I mean, you would, in this picture, to notice that you would have to go all the way from the lowest to the highest region because they don't repeat until the full word level. Like if you only have a model of the letter, you don't have repetition within that. Which is, I mean, an interesting point because we do recognize that there's repetition between this. But technically, if we had learned this whole hierarchy of models, it shouldn't be represented at the highest level, because at the highest level we just represent the 2 syllables.
Right. I think at the highest level you recognize the whole word, right? I mean, you just.
Well, yeah, the parts of the word would be the 2 syllables.
Right. But I'm just saying, you know, even like I know a long word in English, I know how to spell it, but when I read it, I don't care about the actual letter. I just recognize the entire shape of the whole thing.
Yeah.
And that's why that's why it's hard to miss certain spelling errors in the middle if they're just subtle, you know, if the E is swapped for an O or something. If it's not on the end, it's in the middle, it's easy to miss certain things. So it's like we have both models. Like we have a morphology model of the entire word, but we also have a compositional model of it composed into letters, and then we have models of letters, but they can be decomposed into strokes. These models exist in both forms.
So for people who don't really read this language, you would not, the hippocampus would be involved in learning only single characters. But for people who actually recognize it or want to form new words or sentences, the hippocampus would be in the higher level, basically sentences or words. So
Right.
Yeah.
I mean, in some ways, you know, when we read text, it's composed of existing words in novel arrangements. So, and sometimes it's composed of phrases, right? So even, you know, I might recognize this entire phrase. But the point is that whatever component the largest component you can learn or have learned, then the hippocampus is involved in arranging them in new ways.
but we can't really involve the hippocampus in learning all of the little strokes in a larger word. Like if I look at
No, right.
the whole
I
word,
don't.
I can't. Yeah,
No,
yeah.
right.
I'd have
That's
to split it up.
Yeah.
at that point, it's not compositional. The entire word is more of a morphological word. It has a bunch of edges and arrangements relative to each other, and I can learn it as a morphological object.
And is that a limitation of the hippocampus, as in how much memory you can store in there at the same time?
Well, maybe I don't think of it that way. I think it's just obviously it's more efficient overall to be able to recognize larger objects without going the attentional process. I mean, if you want to recognize something quickly, you don't want to have to attend to all its features, right? We want the entire point of, in some sense, of voting and compositional structure is so that you have a much more efficient and faster inference, right? Because in theory, you can infer anything with a whole bunch of low-level compositional objects.
Yeah.
You know,
Like if I only knew the strokes and tried to reproduce this whole thing, it's complicated again because there's like so many strokes to reproduce. But if I kind of recognize this as kind of this grouping as one thing, then it's helpful because okay, now I can actually simplify because I see that this grouping appears here. So as long as you remember, you know, this grouping
but
appears here.
when you were taught to read, did they teach you the individual letters
in elementary school? Yeah.
Yeah. All right. So it's like we learned the letters of the alphabet. That
Yeah.
you learn these three things. You learn the circle and the corner and the half H, and it's no different. It's really no different at all. It's
Yeah.
So can you use the individual components to spell Monty?
Yeah.
That's funny.
Oh, that's cool. So you can use it, yeah, just like letters and phonetically spell.
It's phonetic.
Yeah.
Okay. Oh wow, that actually looks kind of cool.
We should definitely enter a Monty Korean theme someplace, you know.
You notice that in this one, the second syllable T has only two components, this component, that component, and doesn't have like a third one. So this is optional. Yeah.
Is it optional?
It is optional, yes. I mean, not all syllable will have like a third component.
No, but when you're writing out something, you can choose to put it in or not, or is there a proper way to write it?
I mean, it's more of a spelling. Like, I mean, if it's spelled that way, you know, or if I'm just like saying, you know, in English and just like writing what the Korean word is to sound most close, like Monty or like whatever word. And for me, I don't need anything on like I don't need a third component to say Monty.
No, but when I'm writing Korean words, is it
Yeah.
optional? There's a defined method for writing them, or is it like, oh, I can put that letter in or not?
There's a defined way because we
Okay.
have spellings.
Okay, so great, right.
Yeah.
So it's like I could spell something, the word tough in
Yeah.
English. I could spell it TUF, which would be
Yeah.
the phonetically, but the
Right.
proper way is TOUGH, which is
Exactly. Yeah. Yeah. So yeah.
Okay,
Yeah.
the
It's
same
like
idea,
that. Yeah. Yeah.
right?
Anyways. Okay. So I don't know. Hopefully this exercise. I don't know
I
what
think.
to draw from this. It's
Well,
just
I think it's a
yeah.
good. I like it. It first of all, it's a different illustration of something we've talked about a lot, which is Roman alphabets or English, whatever. And it's interesting. First of all, that it's very, very similar. The individual strokes are perhaps even easier to differentiate. It shows that all the issues of hierarchical composition and different levels that we learn these things. It brought up the issue that Tristan brought up, that sometimes we can learn these things as purely morphological objects and not as spellings of letters. And it also shows that what we consider as a one-dimensional language that can be done in two-dimensional letters, which is kind of interesting. I never realized that. So I don't know, it's a nice
Yeah.
little illustration. It doesn't answer any of our questions, I think.
Yeah.
What is the hippocampus? This is probably obvious for neuroscientists. What is the hippocampus time scale that we're talking about? Like, because I can look at this and then look away, and it's like it's in my head. I can reproduce it, right? That was pretty quick, but it was still
Right.
lots of cycles in the
Well, the
neurons.
question is to learn something, that we're still with the basic idea that learning occurs in the synapses between neurons, right? So the question is to learn something is how quickly can you form a synapse, right? That's because that's the substrate of memory. So and it turns out that in most of the cortical tissue, most of the neurons, it takes a fair amount of time to form a synapse. It can be on the order of, it has been as fast as a minute. But typically most people would say slower than that, but even a minute, it's not quick enough. If I look at something and turn away and come back a minute, it's gone, nothing, it's not there anymore. Or they said it still hasn't grown. So we have this theory that, so the fact that we can form these instantaneous memories is inconsistent with the growth of synapses. And which is where we believe most learning occurs. So it has to be modifying existing synapses. And in the hippocampus, there are just a tremendous number of these, what they call silent synapses, which don't seem to do anything, but can be turned on instantly. So they sort of pre-exist, and that they're not doing anything until a chemical process says, flip it like a switch, and that can be instantaneous or very, very fast. So the basic theory is
LTP, right?
Well, LTP is generally refers to more. All right, this is a very confusing topic, right? Most people still believe that learning occurs by modifying the strength of a synapse.
Okay.
And that's how deep learning networks and artificial neural networks works. There's so many problems with that that we don't believe that's true. And I mean, it doesn't mean that there isn't modifications to the long term, but in the basic HTM theory was that most of what happens, you grow new synapses, and what people think about as strengthening synapses is just the permanence of it, how thick it gets, and how long it'll last. So I'm pretty certain that's the vast majority of learning is occurring that way. That you learn slowly, the synapses grow slowly. You can still, but long term. LTP is, long-term potentiation. This idea that, the synapse system value, like, oh, it's 0.2 and now it's going to be 0.3 and it's going to be 0.4. And then that doesn't seem to be possible in biology. It's more like the synapse is not there and now it is there. So it's like more like binary. But if synapse is there, it looks like it's getting thicker with practice, but it doesn't seem to be affecting its value. It just seems to be making it more permanent.
Okay.
I mean, that's in our neuron paper. That's how we spell it. I think it's right. Anyway, so it might be just a quirk of nature. Vivian pointed this out in our last meeting that, in in Monty, we can learn at any speed we want, or we can instantaneously in any region. In biology, that's not possible. And because these silent synapses they're very expensive biologically. So you can't have them everywhere. And so it looks like nature has put them all in the hippocampus, and that's where fast learning occurs. And then the rest of the cortex is much slower and more permanent. But we don't have to stick to that rule. But I do think the idea that there's this hierarchy and we attend, and the different levels of the hierarchy as you're attending, this is probably going to be important for Monty.
It seems generally useful to have slower learning at the lower regions, just so that the input to the higher regions is more stable and doesn't change as much over time.
Right. That's absolutely right. If V1 was constantly learning, then everything above it would be screwed up.
Yeah.
This is why old people like me get set in our ways. It's because we built this foundation many years ago, and our entire worldview is based on this foundation. And I can't change it. Otherwise, I would just be, going back to being an infant again. And whereas, somebody who comes along later in life, they've built a slightly different foundation, which is more modern and more amenable to the current world. And they can say, well, you're old people, just can't, you're stuck in your old ways. Well, it's true.
On that note, fun things. All right, so I'm going to move on from this, and then just maybe in the last few minutes, I can just present what I've written. Again, I think this is just a rehash of what Jeff has written and what we talked about, but hopefully, I don't know. I mean, it will be a win if this sparks any new discussion. So that's my goal. All right.
Yeah.
So I guess this specific example that I was thinking about was, I'm a baby, I don't know what a mug is. I'm trying to learn it. And let's say I'm just using one eye and one hand touching a mug. So, not all parts of the retina is seeing the mug, and then, the left hand is not touching the mug. So if I try to visualize this, so this is all kind of columns in lower level, R1, separated at the primary visual, and the primary somatosensory. So all the green columns are receiving, the sensory input. So not all visual is getting it, but, some are. For the somatosensory, same idea. Maybe the columns that kind of constitute the right hand receive inputs while the left is not. And then I guess I wrote some thoughts that may or may not be true. Likely not true. Okay, so green columns are receiving sensory input, white columns are not. All green columns are learning the mug in the same reference frame, and I think this is established by some higher region or the hippocampus.
Can I just stop right there?
Yeah.
I mean, they all have reference frames for the mug. We're talking about a mug here?
Yeah.
The mug.
Yeah.
But each column in our current implementation, each column independently just defines its own reference frame for the mug. That is, at the moment, there's,
But I thought we were learning at the objects reference frame. So I guess I thought that they were all the same.
Well, maybe the way we implement it in Monty, that's the case.
Yeah.
Right? Because Monty has a different way of doing reference frames.
Well, there would still be separate models, so separate reference frames.
That's true. Yeah. Yeah. But I guess I thought that the coordinates would still be all the same.
Well, again, Monty, it might work this way, but in the biology, a reference frame is defined by anchoring of these grid cell modules. And at the moment, there's no coordination of which grid cell modules get anchored on which cells between columns. I'm thinking there might have to be one. But at the moment, we don't have that in our theory, the biological theory.
Yeah. I think I also had that thought when you were presenting, and I'm like, oh shit, everything after this point doesn't make sense.
Again, this could be something where in Monty, if we understood the problem correctly, and we know what the solution had to be, we could implement a completely different solution that's easier, and maybe it's not confusing at all, but we'd have to basically make sure we understand the problem and that the brain solves this problem somehow, and then we can
Yeah.
solve it differently.
Yeah.
Because it would be trivial to establish the same reference frame for all these different columns in Monty.
Well, it
you know.
depends on what we mean with the same reference frame. Do we mean like the same XYZ coordinate system anchored at the same origin, and there are copies of each of those in each column, or do we mean each column has access to like a global workspace reference frame?
I guess what I meant to say is that each column has to be using the reference frame that it uses for the mug. And so somebody would have to tell the column, implement this reference frame because we're learning mug now.
I guess I was more thinking about so individual columns, in the first sensory input, let's say we learned everything. Each one learns something at 0, 0, 0 at their origin. But when this so in that sense, they don't have the same coordinates because this sum has different features at 0, 0, 0 compared to index, middle, whatever.
Are you holding up your hand? Okay, I wasn't
Yeah, sorry about
okay. Sorry. This one, what the? Okay, sorry.
But so like in my lower regions, we might, let's say in one step we learn something different at origin, but then in higher region, I feel like it should know where these are coming from so they can kind of assemble it in the right, I guess, depending on the spatial orientation of my fingers. Like, so the model in a higher region would be these features would be separated out because it knows that my lower columns are at different locations.
You're losing me. Yeah, I got lost on that one.
Okay, so let's say that like I'm holding the mug. Each of my finger pads are touching different parts. So in each in my index column and my middle column, let's say let's say the index is touching the handle and the middle is the cup. Then let's say like in both of these models, I just the at location 0, 0, 0 or whatever same location, it will store those features. But in a higher column, I feel like it should be able to separate those features in the correct spatial locations because it knows how my two fingers are separated.
I'm not sure. I mean, the words kind of make sense, but the whole picture is still confusing. One of the things I struggle with here, and it's just like, again, I'm struggling, I can't even express it in words very well, is, again, I think of learning as we're learning something new. We're tending to one feature at a time. And the learning has to be, where is that feature in a reference frame? Or where am I in this reference frame? And that feature has to be associated with that location in the reference frame. One at a time. So when I have like two fingers touching the mug, if I'm learning at that point, either I'm going to learn what's going on in one finger or what's going on in the other finger. Or the two fingers are recognizing this is the lip or handle, and then the handle becomes the attended feature. Right? There's got to be this was a surprising revelation to me, but there's really only one attended feature at a time when you are learning something new. So it's hard to keep in mind what's going on with all these central patches because we really can only be, at any point in time, we can only say there is a single feature we recognize, and it's at some location on this model we're building. And yet we have multiple columns active. So I don't, I am confused by this. I don't really understand it.
I mean, if I'm grabbing the handle like this, each finger only knows, I mean, to each finger, all the features are, let's say it's like a just flat handle, then it's just all the same features. But in a parent column, we can arrange those features spatially because we know the fingers are.
Well, I don't think that's the way it works. I don't think that's the way it works. I think the way we've defined this, Hojea, is that imagine that we're talking about some S1 getting input from the different fingers, some out of century one.
Yeah.
Each one of those columns, after it's been trained, has a model of the handle or the bug. And each one gets some input. Each one knows where it could be on the object. And therefore they vote together and they say, we are on the bug or we're on the handle. And that is the thing that's passed up. There's no simultaneous multiple child objects being passed up. It's just one at a time. And that's the way I view it. I may be wrong. That's the way I've been viewing it for a long time. And so the multiple ones have to work at the same level via voting, and then you pass up one thing. You don't pass up multiple things. You say,
okay.
we reach the consensus. This is the handle. You do, and the next region up says, I'm giving you a handle. I'm not giving you
like individual feature. Yeah.
Yeah.
You're giving the object ID. Yeah.
Right. And again, it goes to this idea. Imagine attending to this. You're trying to learn something. If you're learning, you can only attend to one thing at a time. So I can't touch the cup. Imagine it's a new shape I've never learned before. I can't touch the cup with multiple fingers and simultaneously learn that. I have to imagine one sensation in one location. I can't move two fingers over the cup simultaneously and be learning. I just can't do it. You have to basically attend to one thing at a time, move it around.
Can we look at it and touch it at the same time and be able to build a model of?
Right, you can, but that's interesting there. That's a really good observation, because if I'm looking at it and touching at the same time, it is the same feature that's being passed up. It's like I'm looking at the same place my finger is touching. I can't learn an object by attending visually to one part and attending tactily to another part. I gotta pick one or the other, or I could attend visually and tactily to the same location, which we typically do. And then move that attended location around. So in the end, they are still getting one sort of common feature. That feature is being recognized both visually and tactily or somatosensorily.
And is that feature object ID? Because
it's an idea of whatever it can recognize.
Okay.
It's an object in the sense that if multiple columns are voting, it's an ID of some sort, whether it's the whole mug or just a handle or some component. I don't know.
Yeah.
It's a kind of a strange thing to realize that only one thing can be attended to at a time while learning. Or you even just any attention, you can only attend to one thing at a time. The brain can process multiple things at a time if you're not attending to them. Like that was the example of me driving the car and doing all these things, but not attending to it while I'm attending to my conversation or attending to something else. But this learning process where you're dealing with novelty, it's one thing at a time. I mean, unless somebody can come up with an example that says otherwise.
Yeah.
So playing the piano with two hands, because I don't know how to play the piano, so I recently struggled with I keep alternating between focusing on the right hand and the left hand.
Right.
And then after a while, once I started to understand that they both are part of this one, one sheet, one song or whatever, it started to make sense that I was able to start playing both hands at the same time. But only when I started thinking of them as being like two child actions of one object, one larger object.
But you can't attend to them both at the same time, right? You had to learn by attending to one versus the other, right? Until you build up some sort of model. And this is what when you start learning to play piano, you start at one note at a time. And then you can learn there's triads, and there's minor and major triads, and so you can learn those as an object. Or you can learn certain motifs of a series of notes, the triplets or whatever you want, but you can only attend to one thing at a time. I think that's still true, right? If you try to attend to what your hands are doing, you can't attend to multiple parts. You can play multiple things at once. You can use your two hands, many fingers moving, but this is, by the way, this is really interesting because, again, this is like a tie-in between the problems of inference and learning with behavior. Behavior is exhibiting these same issues that we're having with inference and learning, that when you learn the behavior, you have to attend to one thing at a time, and then later you can do multiple things at once as an object, you know.
Yeah.
You know, like really a professional pianist, they can look like several bars of music and recognize it as something. They don't have to look at all the notes. They don't look at the notes. They recognize it as a complex object that they know how to play back. And that's why they can play so fluidly, right? They don't look at the notes.
Yeah.
It's like reading text and not looking at the letters. But it's even more complex.
But then how does Hippocampus do fast learning? So I guess like another idea that I put here was that, you know, if we're learning with an eyeball and a finger, and, you know, let's say that we're looking at the same location, the eye will have like a model with color information. The finger will have the same model, but, you know, I don't know, with tactile information. But the hippocampus will somehow get both. It has a richer model.
But if the model has to be a single model that's passed up, a single child object, right?
Right.
So,
I guess I generally have a question of like what information gets passed, and I know that we're converging to like some kind of agreed ID or voted.
It's
thing,
an ID,
but,
right? The ID does not contain color. It doesn't contain anything. It basically says that there is something recognized in the visual space, something recognized in the tactile space. Those two things have been associated, so it's one pattern that's being passed up. It can be broken. You can, as it affects the visual columns and the tactile columns, you can break it further apart. But it's just one. It's just one SDR that's being passed up. As this is something that the columns below have agreed upon that they're seeing or sensing.
But it can get input from two different regions, like from vision and sensory at the same time.
Right, but I always viewed that as that those guys are voting, and so they reach a consensus through voting. It's the same voting layer. That's how I've always viewed that. You know, now in our hierarchy paper, the connections are a little bit more subtle than we originally assumed. But let's keep going with this idea that you have, you know, I'm a column, I'm a tactile column, and you're a visual column. You form an SDR for the thing you're sensing. I'm forming an SDR for the thing I'm sensing. Those two SDRs are there's no coordination between us. But then because they're the same thing in the real world, we form associative links between the two. So if I invoke my SDR, it'll invoke your SDR. If you invoke your SDR, it'll invoke my SDR. And if someone else like the hippocampus is looking at it, it can sample randomly from cells in both columns. It doesn't make any difference. It's basically it becomes one SDR at that point.
Like kind of gets morphed into like
it's a single thing now.
It's its own separate SDR that's maybe somehow based on.
It's just the concatenation of the different columns SDRs. It's not like a new one. It just turns out that if you want to recognize something, that you have an SDR and I have an SDR, I don't have to look at yours and mine. I can just, as long as those two are associatively linked. So when yours is active, another one's active, I can randomly sample between those two. It doesn't make any difference, and I'll get the same result statistically. It's a strange idea, but it works.
And does it work? I guess my last kind of point was to kind of, does this work backwards? As in, you know, this point about if I see a mug, then I should have a sense of, you know, what it should feel like when I touch it. And, you know, if I touch it, then I should have a sense of what it would look like. But it doesn't necessarily mean that the vision column and the finger column have the same exact model. Because the finger column shouldn't. Yeah, if the finger column doesn't have color information.
They don't have the same model at all.
Okay.
They don't have to. All they have to do is say that your model is coincident with my model. That is, they both happen at the same time in the same place.
I see. Okay.
So, like, if I were passing down an SDR representing the object, when it gets to the vision column, it'll invoke the vision column's model of that object, and when it gets to the tactile column, it'll invoke the tactile column's model of that object. but there's no information about the details of those models in the SDR that's being passed down.
Right. Yeah.
It's just a way of invoking the correct model of the child.
Yeah.
Just like in Monty, the models never get communicated between columns.
Right.
Only the IDs and poses of them.
Yeah.
Right.
And those don't contain information about the individual features or the shape or anything
Right.
like that of the object.
Yeah. Yeah. I need to kind of think more in terms of kind of the association and the IDs. But yeah, this clarifies a lot of things. Because I think I was confusing myself on like, I feel like I'm passing too many features and this feature doesn't fit in that column.
There's no features. No features
Right.
it's just IDs. That's it. It's just associations. I mean, we've had this discussion, Rami and I, about whether SDRs have they contain more details, information in them. And I say no, and Rami says maybe, or yes, I'm not sure. But I'm still going with the idea that the SDR really doesn't contain anything else. It's just a bit pattern that can be associated with other bit patterns. So it's not conveying any. You can't look at it and say, oh, what does this mean?
Yeah.
You can just look at it and say, oh, what does this invoke elsewhere? then that tells you what it means.
I have a question about the SDR sampling. So the reason I'm asking this is because it seems like if we just have IDs, when we think of like in Monty, where we have just ID, which is just think of it as a number. Here's an ID, here's an ID. It doesn't support, like, if we were to do any sort of sampling, like SDR samples, we would essentially be picking random bits from those ID numbers. Like in the idea of sampling, like Jeff says, where you have two SDRs and let's say they're fixed length, and we want to sample into a combined SDR, which is also fixed length, then we're just picking some bits from one, some bits from the other. But that means that the sampled one, the one that is sample of both of them, has some properties that imply the likelihood of the other one being present, versus in a way where just using number IDs does not. Like there's a correlation between the sampled ID or sampled SDR. It will only get triggered if one of the other ones trigger. But in the representation there is encoded the correlation between the two lower one is encoded in the representation of the SDR.
Well,
whereas
you could say it's encoded, but it's not extractable. I mean, you can't.
No, it's not extractable, but it's there.
It was derived from two
right.
smaller SDRs. But I can't go backwards typically.
Right. Agreed. Well, and what I'm saying is if we just think of in Monty where we just use random numbers, that means that if we have sampler, it needs to be derived from the other two IDs. We can't just pick a random number, is what I'm saying.
Well, you're saying you can't sample, right? Because if you're using dense representations like an integer, you can't sample from it because every bit's important. Right.
Right. And that's problematic because then if we pick a random ID.
Why is it problematic?
No, I guess what I'm trying to say is if we pick one of the other, like lower level ones, lower level A and lower B, if we just say lower A, just because the upper learning module gets lower A, there's nothing in that lower A saying, and there was likelihood that lower B is active right now. Or if we just pass up lower B.
Wouldn't you have to pick the exact same ID number for the lower A and lower B? You'd have to have the exact same. You'd have the exact same ID. All these ideas of distributed representations.
Right, but we're not passing two IDs to the top one. We're passing one, and if we just pick one or the other, we're losing information.
Right, you'd have to. It seems like you'd. I don't know how Monty does it. So someone's.
Wait, can I clarify the scenario right now? Is when you say
we have
two at the lower level, we have like two sensors that are both inferring the same object?
No, two lower level modules and then one higher level module. Like
the two lower modules,
like
but they are sensing the same object, right?
Yes, vision and touch.
right?
Okay.
Lower level module for vision, lower level module for touch. Lower level
they're
module
both-
for vision has ID A. Lower level module for touch has ID B.
But wouldn't they have to have the same ID at this point? They'd have to have the same ID.
No, they learn their own IDs, right? It's random
but-
SDRs.
But it
Well,
won't work.
in the current version of Monty, it's they need to have the same ID for voting to work, but that's
Okay,
not
so never mind. So we'll come to this problem later.
Yeah.
Let's
Well,
not worry about it.
I think it's just something that's always been a little bit nervous for me is, when we go away from SDRs to using, binary integers, whatever we're using, you lose some properties that SDRs have. But we don't know if those properties are essential. So far Monty is working okay without those properties.
Yeah,
but-
I mean, me saying that Monty has to have the same IDs doesn't mean that
Yes.
this is how I think it should be. It's just this how it is today. So I think the points you're bringing up, Tristan, are still interesting to think about once we change to them actually being able to represent objects with different SDRs.
Do you think that we have to go there? I know we've talked about this in the past, but not recently. Do you think we're gonna have to go there, or how far can we go with Monty using?
Well, I think, yeah, eventually if we want to do more complex things like association between, for example, language and a touch model and a vision model, I think, yeah, we need that. And also if we're learning in more complex environments where we can't supervise the columns, like we can't tell each column, you're sensing this object now, then
Right.
there's no guarantee that they will learn the same object IDs.
Right. All right. And I've always been concerned about this transition from going from these, non-SDRs to SDRs, but Vivian, you always say it's not a problem, right?
Well, I guess those are two separate things, maybe. Whether we use like an integer representation versus SDR is one question, and then the other one is whether we require each column to use the same ID or SDR for the same object, or if they can use arbitrary IDs and SDRs, and then we learn associative connections.
Okay, so maybe, one of the things that seems that happens is I can have an ID SDR that can be associated with two different SDRs elsewhere, right?
Yeah.
And this happens naturally. If I did it with integers, I'd have to have some sort of associative table lookup or something. I don't know.
Yeah.
Something like that.
Yeah, that's the problem, and it's gonna blow up. So yeah, we all agree on the problem and the solution. I think.
I hope it doesn't blow up.
Well, that associative table is way more inefficient than an SDR or something, or a derivation.
Maybe, I don't know. Computers are pretty fast.